In this video, we're going to be talking a little bit about mathematical modeling with some exponential and logarithmic equations. What I'd like you to do is take a look at the data that I've given you here. The data models the age of a tree in years and its height in feet over a series of years. And I'd like you to do a few things. Start by putting this information into Desmos and determining a logarithmic regression model that represents this data, and then graph the equation. Once you've graphed it, we want to decide whether or not the equation is a good fit. You can see I've put the data into Desmos, and using regression, I'm going to pick a logarithmic model. See there, my graph is now showing up in orange. Let's just turn on projector mode so it's a little bit easier to see. And using this model, I can get a r-squared value of about 0.988. You can see my parameters there. So this is probably a pretty good regression model. We can try some others, but they might not make very much sense. Let's try a quadratic model. So there's a quadratic model, and looking at the fit, the quadratic model does fit our data a little bit closer. It's 0.99 for an r-squared value. But if we think logically about the situation we're modeling, the growth of a tree, if we pick the quadratic model is telling us that the tree starts to grow, and then all of a sudden it gets to this point where it doesn't grow anymore, it instead starts to shrink. Whereas the logarithmic model, the tree was planted and it grows pretty quickly in the beginning, and then it starts to slow down and level out. So I think our best model right now to use is our logarithmic model. So next question is asking us to interpolate the data. Interpolate means to find a value inside the range of data that we've been given. So we've been given a range of data between 1 year and 11 years. The question is asking us to interpolate the average height of the trees at 1 1/2 years. So you really have two options for doing this. We could look at our equation, and we could look at our parameter values, and we could fill these parameter values in for A, K, H, and C, and then we could evaluate this on a calculator. So at 1.5 years, that would be our x variable. So I could plug in 1.5 for x and try and find y. But since we're working with Desmos, we have an easier way to do this. I can just plot the line x equals 1.5. And I see that horizontal line show up. And Desmos tells me where the lines cross, and they tell me that intersection value, that point of intersection. So at 1.5 years, interpolating, the trees were about 8.6 feet tall. Extrapolating means to find information that is outside of the set of data. So we're extrapolating, we're predicting the height of the tree when it's 20 years old. Back to Desmos, and this time I'll type in a value of x equals 20 years, and Desmos is telling me that at 20 years the tree's about 23 feet tall. And so we can talk about if we think this prediction is accurate. And if I look at my data, well, as the trees get older and older and older, they still keep growing, and that might not be the most accurate model to predict this. So I think they probably start to level off a little bit more. Maybe saying it's 23 feet tall is accurate, but I think we might want to aim for a little bit less. And I would say, based on our observations of the data, the trees are going to level out, and they're going to be probably between 24 and 24 feet tall. I don't think, like our model predicts, if we go for infinite time, that the trees could be 100 years old and continue to grow. They usually just level off. So that's just a little bit more on how we can use Desmos to help us model data and make predictions. We're going to keep working with regression as we continue on this semester. Let's try a slightly different question. Let's say we have, to invest money, we have $50,000 to invest, and we're provided with two different options. Option A is earning 6.25% interest compounded annually with a penalty of 2% of the principal if the money is withdrawn before 10 years. And option B, 6% interest compounded semi-annually with no penalty. So we'd like to construct a model that determines the amount as a function of time for each investment, and then see if we can figure out, if we withdraw our money once we have $80,000, which investment would allow us to do this the fastest. So a tricky question. In option A, when we invest our principal amount, we're going to earn 6.25% interest compounded annually, so we're going to earn 0.0625% interest compounded annually for an unknown amount of time. But we also have to try and factor in this penalty. Penalty would be taking away 2% of the principal, but only if we're investing it for less than 10 years. So if we know our investment's going to last longer than 10 years, we can kind of exclude this part. But for now, we'll keep it in. So simplifying, my final amount is going to be equal to my principal times 1.0625 raised to the power of n minus the 2% of my principal. Option B, my final amount, would be equal to my principal times 1 plus, now here, since this is compounded semi-annually, my interest rate, which is 6%, gets divided by the number of compounding periods in a year. Semi-annually means twice. So my per compounding period interest rate is 3%. Raised to the power of, now I've made a mistake, my variables for years is supposed to be t. So raised to the power of t years, but I'm compounding twice a year. So that'll be raised to the power of 2t. So simplifying, my final amount is equal to my principal times 1.03 raised to the power of 2t. So let's put both these equations into Desmos and see what happens. So my first equation, my principal was $50,000 times 1.0625 raised to the power of t, in this case x, variable x, minus the 2% of the principal. Let's try and zoom out. You can see that. Putting in my second equation, y equals 50,000 times 1.03 raised to the power of 2t. You can see both equations increase at essentially the same rate. Let's just throw in one more value, y equals $80,000. Trying to find out when we reach that mark. Let's zoom in. You can see so they both start with the same amount, but notice how the green curve, because of that penalty, does start a little bit lower. And then it's really hard to see their differences. Let's just get Zoom in as close as we can. Looks like my purple line will make it to 80,000 first. So my purple line would be option B, the one with no penalty. After about 7.9 years, you get to $80,000. Compare that to my option A. That's about after 7.96 years, you get to $80,000. So really the difference is barely anything. But option B will make it to 80,000 first.